big stuff, small stuff.
Uh-huh.
But have you ever like really stopped to think about what makes stuff?
Yeah.
Well, today we are going to be diving into one of the most fundamental properties of matter.
Right.
It's something that is so intrinsic that it actually governs everything from the tiniest quarks to the most colossal neutron stars.
It's true.
It's something you probably don't think about over your morning coffee,
No, you don't.
but it is absolutely key to how the universe works, and that is quantum spin.
Yeah, you got it. And this is not just another, layer of physics. It's like woven into the very fabric of reality.
Right.
It really is. And we've got all this great material to work with today. And our goal is to unpack this concept of quantum spin for you.
Right.
We are going to explore what makes it unique, the powerful theories that explain it,
Yeah.
the really ingenious experiments that actually proved it was real, and the truly wide-ranging impact that it has both on our understanding of the cosmos and the technologies that are shaping our future.
Yeah.
So think of this as your express route to getting a really solid handle on this concept.
Okay, so quantum spin. I mean, just the name kind of conjures up an image in your mind of something like whirling around like a top.
Yeah.
But everything that we have been looking at makes it clear that's not actually what's happening.
Right.
So if it's not physically spinning, then like what in the quantum world is spin?
That is a great question, and it really is at the core of this topic.
Yeah.
Quantum spin is an inherent form of angular momentum that every fundamental particle,
Right.
and even, composite particles like protons and neutrons has,
Right.
it's as fundamental to them as their mass or their electric charge.
Okay.
And unlike a spinning planet,
Yeah.
it's important to remember that a particle has this spin even when it's completely at rest. So this is really where the quantum chair shines through. And there's really no equivalent in our everyday experience that can fully capture what it is.
So it's basically a built-in characteristic that's always there at that subatomic level.
Right.
Okay, so one of the first things that jumped out to me from all the material we've been looking at is this idea that spin is quantized.
Yes.
What does that tell us about it?
Yeah, that's a great point to bring up. Quantization is truly, it's like a signature of the quantum realm.
Right.
And it means that a property can only exist in very specific, discrete amounts,
Okay.
like steps on a staircase,
Uh-huh.
rather than a smooth ramp of possibilities.
I see.
So with spin, both its overall strength or magnitude and how it aligns along any chosen direction
Okay.
are quantized. And it's much like, how an electron's orbit in an atom can only have certain energy levels?
Right, so this is where those quantum numbers come into play.
Exactly.
We have the spin quantum numbers.
Yes.
What's the story with that one?
So the spin quantum numbers, as you said, it is a fixed value for each type of fundamental particle.
Okay.
And it determines the total amount of spin angular momentum it has.
Gotcha.
And what's really interesting is that Kamens can be either a whole number,
Okay.
like 0, 1, 2,
Uh-huh.
or a half whole number, like
Yeah.
1/2, 3/2, 5/2, and so on.
Okay.
And this is a key distinction from the orbital angular momentum quantum number, L, which can only be an integer.
Half integer spin. That feels so strange, like intuitively from our everyday perspective.
It does.
Is there like a reason why it can take those half values?
At a fundamental level, it arises from the mathematical framework of quantum mechanics
Okay.
and the way spin transforms under rotations.
Hmm.
So while a full explanation would get quite technical,
Yeah.
think of it as a deeper symmetry
Okay.
that's at play in the quantum world.
Okay.
That doesn't have a direct parallel in classical physics.
Yeah.
So, for example, electrons, protons, neutrons, and quarks all have a spin quantum number of s equals 1/2. Then you have particles like the photon with s equals 1 and the Higgs boson with s equals 0.
Gotcha. So S gives us that total quantity of spin.
Right.
But the material also mentioned a spin projection quantum number m's.
Yes.
So what is that one all about?
So the spin projection quantum number m's describes the orientation of that spin angular momentum vector
Okay.
along a specific axis, usually designated as the z-axis.
Okay.
And for a given value of m's can take on values that range from negative is to positive is in integer steps.
Okay.
So if a particle has a spin quantum number s equals 1/2,
Right.
then m's can be either plus 1/2 or minus 1/2.
Okay.
And these two possible orientations are often referred to as spin up and spin down.
Gotcha.
And this gives us a total of 2 s plus 1 possible orientations for the spin.
Okay, so two orientations for an electron. I'm guessing this is going to have some big implications down the line.
It will.
All right, so we've established that it's quantized, it's intrinsic, and the material also touches on the mathematical description using these vector operators. Is that just basically like a fancy way of saying that it behaves like angular momentum?
In essence, yes.
Okay.
The fact that you can actually describe spin using mathematical tools that we call vector operators.
Right.
And they're denoted as x, psi, and ses.
Okay.
And these obey the same fundamental mathematical relationships, which we call commutation relations, as the operators for orbital angular momentum Lx, he, and Lz.
Right.
That provides a very robust mathematical confirmation that spin is indeed a form of angular momentum.
Okay. So this next part seems really fundamental.
Okay.
Our sources emphasize how the spin quantum numbers acts like a key to classifying particles.
Yes.
Into two very different groups.
Yeah.
Fermions and bosons.
That's right.
Can you lay out that distinction for us?
Absolutely. The value of a particle's intrinsic spin actually dictates its fundamental statistical behavior.
Okay.
Essentially how multiple identical particles can occupy the same quantum state. So first let's talk about fermions.
Okay.
Fermions are particles that have half-integer spin quantum numbers.
Right.
So that's s equals 1/2, 3/2, and so on.
Gotcha.
And the particles that make up ordinary matter like electrons, protons, neutrons, and quarks are all fermions.
Okay.
With a spin of 1/2. Neutrinos are also in this category.
Okay.
And a defining characteristic of fermions is that they obey Fermi-Dirac statistics.
Okay.
And crucially, the Pauli exclusion principle.
Oh, yeah, the Pauli exclusion principle. That sounds like a rule with some very serious consequences.
It is.
What exactly does it tell us?
It's a remarkably simple yet incredibly powerful principle that states no two identical fermions can occupy the exact same quantum state simultaneously.
Okay.
So think of it as a fundamental need for personal space at the quantum level.
I like that.
This principle is the reason behind the shell structure of electrons in atoms.
Yeah.
Because each electron in an atom is a fermion with spin 1/2.
Right.
Only two electrons, one with spin up and one with spin down, can occupy the same orbital.
Okay.
And this arrangement of electrons in different energy levels and orbitals governs the chemical properties of elements and how they bond to form molecules.
Yeah.
So in a very real sense, it's the foundation of chemistry and the complexity of the periodic table.
Wow.
It really is. Furthermore, it's essential for the stability of matter itself.
Right.
Without it, all the electrons in an atom would try to cram into the lowest energy level.
Yeah.
And that would lead to a very different and likely unstable universe.
I see.
It also plays a critical role in extremely dense environments like white dwarf and neutron stars, where the Pauli exclusion principle provides the outward pressure that prevents further collapse against immense gravitational forces.
So basically the fermions are saying like, hey, we can only be packed so tightly.
Exactly. It's like a quantum traffic jam.
Yeah.
You can only fit so many in.
So the very stability of the stuff around us, like right down to how atoms are built,
Yes.
hinges on this half-integer spin property?
You got it.
That is mind-bending.
It is.
Okay, so what about that other class, the bosons?
So bosons are particles with integer spin quantum numbers.
Okay.
So s equals 0, 1, 2, and so on.
Right.
Familiar examples include photons, the particles of light with spin 1.
Okay.
Gluons, which are the force carriers of the strong nuclear force, also spin 1. The W and Z bosons mediating the weak nuclear force spin 1.
Okay.
And the Higgs boson with spin 0.
Gotcha.
Interestingly, some composite particles like mesons, which can have spin 0 or 1, and alpha particles, which have spin 0, also fall into this boson category.
Okay.
And the key difference here is that bosons obey Bose-Einstein statistics.
Okay.
And unlike fermions, multiple identical bosons can occupy the same quantum state.
So they're much more communal.
Yeah, they're very social particles.
Yeah.
They like to hang out together.
And this leads to some extraordinary phenomena.
It does.
So give us some like tangible examples of this quantum clumping.
So think about lasers.
Okay.
The incredibly intense and coherent beam of light from a laser is a result of a vast number of photons, which are bosons with spin 1, all crowding into the same quantum state.
Okay.
They're all sharing the same energy momentum and even spin orientation.
Wow.
Another striking example is Bose-Einstein condensates.
Okay.
When you cool certain bosonic atoms down to temperatures near absolute 0, A large fraction of them can collapse into the lowest quantum state, essentially behaving as a single macroscopic quantum entity with really bizarre properties, like superfluidity, where they can flow without any resistance.
So it's like fermions are all about individuality, and they contribute to the stability of matter.
Yeah.
And bosons are all about togetherness and collective phenomena, often related to forces.
That's a great way to sum it up.
Yeah.
They're very different in their behavior.
So now let's switch gears a bit.
Right.
Our sources delve into the theoretical foundations of spin. And it sounds like initially the idea of spin was kind of added in just to explain experimental results.
Yeah, that's a fair initial take on it.
Okay.
While the concept of spin was indeed proposed by George Uhlenbeck and Samuel Goudsmit to account for puzzling experimental observations, like the anomalous Zeeman effect and the fine structure observed in atomic spectra.
All right.
And this was building on Wolfgang Pauli's earlier suggestion of a fourth quantum number for electrons.
Okay.
Its deeper and more elegant theoretical grounding emerged with the development of relativistic quantum mechanics.
And this is where the famous Paul Dirac comes in.
Exactly. In 1928, Paul Dirac set out to formulate a quantum mechanical equation for the electron that would also be consistent with Albert Einstein's special theory of relativity. And the outcome was the remarkable and profound Dirac equation. And what's significant is that spin wasn't something that Dirac had to manually insert into his equation. It arose naturally and inevitably from the mathematical structure of the theory itself.
So spin was inherently part of this relativistic description of the electron.
Precisely, the solutions to the Dirac equation weren't the simple wave functions of non-relativistic quantum mechanics. They were more complex mathematical objects called four-component spinors. And these spinors inherently contain the degrees of freedom that we interpret as the spin 1/2 property of the electron. Moreover, the Dirac equation also correctly predicted the magnetic dipole moment associated with the electron spin, a feature that had to be added as a separate assumption in earlier non-relativistic theories. And what's even more profound is that the Dirac equation also predicted the existence of antimatter, specifically the positron, as another consequence of reconciling quantum mechanics and relativity.
So spin and even antimatter emerging naturally from a single theoretical framework.
Yes. It's incredible.
That's amazing.
Yeah.
Our sources also mention this connection between spin and the symmetries of spacetime.
Yes.
Specifically, the Poincare group.
That
sounds pretty abstract.
It is an abstract concept, but one that speaks to the deep interconnectedness of fundamental physics. So special relativity describes the symmetries of spacetime through what we call the Poincare group, which includes transformations like rotations boosts, which are changes in velocity, and translations in space and time. And in the framework of quantum field theory, fundamental particles are viewed as fundamental representations of this group. So you can think of these representations as mathematical blueprints that dictate how a particle transforms and behaves under these space-time symmetries. And crucially, these representations are characterized in part by their mass and their spin.
So in this sophisticated picture, spin becomes a fundamental label, intrinsically linked to the underlying symmetries of the universe, as described by relativity.
That is mind-bending in like a really fascinating way.
It is deep.
Now we can't talk about spin without mentioning the spin statistics theorem.
Right.
Our sources call it a profound result.
Yes.
Why is that?
Well, the spin statistics theorem is truly a cornerstone of modern physics. It's a rigorous and deep result within quantum field theory that firmly establishes the fundamental connection between a particle's intrinsic spin and the statistics it obeys, whether it's a fermion or a boson. It states without exception that particles with integer spin must be bosons. And particles with half-integer spin must be fermions. And this isn't just an empirical observation that scientists noticed. It's a necessary consequence arising from the fundamental principles of relativistic quantum field theory.
So this isn't just some abstract mathematical curiosity.
No, it's not. This has real and tangible implications for how the universe behaves.
It does. The theorem is upon very fundamental principles. Lorentz invariance, meaning the laws of physics are the same for all observers in uniform motion. Locality, which is the principle of causality, meaning that an event cannot be influenced by events outside its light cone. And the positivity of energy, the vacuum state, is stable and has the lowest possible energy.
Okay.
So the spin statistics theorem essentially solidifies the deep and unavoidable link between a particle's most intrinsic quantum property, its spin, and its collective behavior when you have multiple identical particles.
Okay.
It fundamentally explains why fermions are governed by the Pauli exclusion principle, and why bosons can all occupy the same quantum state.
Gotcha. So these seemingly out there theoretical ideas have concrete and essential consequences.
They do.
For how matter and energy interact at the most fundamental level.
Absolutely.
That is so powerful. So now let's shift our focus to how we actually know about spin.
Okay.
Our sources highlight some really ingenious experiments.
Yeah.
And the Stern-Gerlach experiment seems particularly groundbreaking.
It really was a landmark experiment.
Yeah. Can you walk us through the basic setups of what they observed?
So Otto Stern and Walter Gerlach took a beam of silver atoms.
Okay.
And they're significant because they have a single unpaired electron in their outermost shell.
All right.
And the angular momentum of this atom is largely due to the spin of this electron.
Okay.
They then pass this beam through a specially designed inhomogeneous or non-uniform magnetic field.
Okay.
And classically, if these atoms possessed randomly oriented magnetic moments, you would expect the beam to be broadened into a continuous smear as it traveled through the magnetic field.
Okay.
This is because each atom would experience a slightly different force, depending on its magnetic moment's orientation.
Right.
But that's not what happened.
So it was a much more distinct result.
It was, instead of a continuous spread, the beam of silver atoms split into two distinct, well-separated spots.
Wow.
Yeah, and this observation directly implied that the magnetic moments of the atoms, and therefore the spins of their outermost electrons, could only take on two discrete orientations relative to the direction of the magnetic field. This was a beautiful and direct confirmation of the idea of spin quantization. And specifically for an electron with a spin, quantum numbers equals 1/2. The two possible values of m's plus 1/2 spin up and minus 1/2 spin down. The inhomogeneous field is crucial here because it exerts a force on the atoms proportional to the component of their magnetic moment along the field gradient, leading to that spatial separation of the beams with different spin orientations.
So that must have been like a really revolutionary result at the time.
It was groundbreaking.
What other experimental evidence supports the idea of quantum spin?
Well, the fine structure observed in atomic spectra provides another crucial piece of evidence. When you examine the spectral lines emitted by atoms with very high resolution, you find that many lines are actually split into closely spaced doublets or triplets. And this fine structure arises from the interaction between the electron's intrinsic magnetic moment due to its spin and the magnetic field generated by its own orbital motion around the nucleus. This interaction, known as spin-orbit coupling, results in slightly different energy levels, depending on the relative alignment of the electron's spin and its orbital angular momentum vectors, leading to that observed splitting of the spectral lines.
And there's the anomalous Zeeman effect.
Yes.
That sounds like something that initially didn't quite fit the existing theories.
Exactly. When atoms are placed in an external magnetic field, their spectral lines undergo further splitting. And this is known as the Zeeman effect. However, the patterns of splitting that were observed experimentally
were often more complex or anomalous than what could be predicted based solely on the interaction of the external magnetic field with the electron's orbital magnetic moment. It was only by incorporating the concept of the electron's intrinsic spin and its associated magnetic moment that physicists were able to develop a complete and accurate explanation for these intricate splitting patterns.
So these really detailed observations of light emitted by atoms, alongside that direct measurement in the Stern-Gerlach experiment, really solidified the physical reality of quantum spin.
It did.
Now, our sources also suggest that the success of the Pauli exclusion principle itself provides indirect yet compelling evidence for spin.
That's absolutely correct. While the Pauli exclusion principle doesn't directly measure the spin of a particle, its incredible success in explaining the structure of the periodic table of elements and the nature of chemical bonding
provides very strong indirect support for the existence of an additional quantum number for electrons beyond the orbital ones, an L and L. This fourth quantum number, as we now understand, is the spin projection quantum number HEMS, with its two possible values, +1/2 and -1/2, allowing for a maximum of 2 electrons with opposite spins to occupy the same atomic orbital.
Gotcha.
And without this principle, which relies on the fermionic nature of electrons due to their half-integer spin, our understanding of chemistry would be fundamentally flawed and unable to explain the observed properties of the elements.
So spin is definitely real. It's quantized in these specific ways, and we've got a solid body of experimental evidence to back it up.
We do.
Okay, now let's get into the spin magnetic moment. Our sources explain that charged particles with spin also possess an intrinsic magnetic dipole moment. Why does this happen?
So classically, we know that a moving electric charge generates a magnetic field. And while quantum spin isn't a physical movement of charge in the classical sense of something orbiting, it is an inherent form of angular momentum. And any form of angular momentum associated with a charged particle gives rise to a magnetic dipole moment. So you can think of it as an intrinsic magnetic field that is generated by the particle's fundamental spin.
So there's like a mathematical relationship that links the spin S to this magnetic moment.
That relationship is expressed by the equation is equals G's times Q over 2m times S, where Q is the electric charge of the particle, m is its mass, and G's is a dimensionless quantity known as the spin G factor. And this G factor is a particularly important and revealing quantity.
What's so special about this G factor?
So our sources mention that the Dirac equation predicts a value of exactly 2 for the electron. And that's a very significant prediction of the Dirac equation in its relativistic description of the electron. The equation naturally leads to the prediction that the electron's spin G factor should be precisely 2. This was a major triumph for the theory. However, incredibly precise experimental measurements have revealed a very slight but definite deviation from this value.
And this tiny discrepancy is where that more advanced theory of QED comes into play.
Precisely quantum electrodynamics, which is our most successful and precise theory, describing how light and matter interact through the exchange of photons, provides an even more accurate prediction for the electron's G factor. QED takes into account the effects of virtual particles, which are fleeting quantum fluctuations in the vacuum that constantly interact with the electron. And these interactions lead to tiny corrections to Dirac's prediction. QED calculations yield a value of approximately 2.002319 and so on. Which is an astonishing agreement with the most precise experimental measurements ever made. This remarkable agreement is one of the most stringent tests and greatest triumphs of all of science, highlighting the incredible accuracy of QED.
So this minuscule deviation from 2, known as the anomalous magnetic moment, is a really big deal in terms of testing the limits of our fundamental theories.
It is.
And this magnetic moment, our sources say, is absolutely crucial for technologies like NMR and MRI.
Absolutely. The interaction of these intrinsic spin magnetic moments with external magnetic fields is the fundamental principle behind both nuclear magnetic resonance and magnetic resonance imaging. These technologies leverage the fact that the nuclei of certain atoms, such as hydrogen in water, which consists of a single proton with spin, possess a magnetic moment. And by placing these atoms in a strong external magnetic field, and then applying carefully tuned radio frequency pulses, we can manipulate the orientation of these nuclear spins and the way these spins respond to these pulses and then relax back to their equilibrium state. Provides a wealth of information about the molecular environment in NMR, allowing us to determine the structure and dynamics of molecules, or about the anatomical structure and function of tissues in MRI, giving us those detailed medical images. It's a beautiful example of how a fundamental quantum property underpins such powerful macroscopic technologies.
It's incredible to think that this seemingly abstract quantum property is at the heart of such vital diagnostic tools in medicine.
It is.
So our deep dive wouldn't be complete without exploring the broader implications and applications of spin, extending beyond just our understanding of individual atoms. And our sources really emphasize its fundamental role in the structure of matter itself.
Yes. As we discussed earlier, a particle's spin dictates whether it's a fermion or a boson.
Right.
And this classification, particularly through the Pauli exclusion principle for fermions, underpins the very structure of atoms, how they form chemical bonds to create molecules, and ultimately the macroscopic properties of all the solids, liquids, and gases that make up our world.
Right.
Without spin and the Pauli principle, the universe as we know it, with its diverse array of elements and compounds, simply could not exist.
And when we move to the realm of particle physics,
Yes.
spin continues to be a key characteristic for identifying those fundamental particles.
It does. Spin is a fundamental quantum number that serves as a primary way to classify all the elementary particles within the Standard Model,
Right.
which is our current best theory describing the fundamental building blocks of the universe and the forces that govern their interactions.
Yeah.
Spin determines not only what kind of particle it is, fermion or boson,
Right.
but also how it interacts with other particles.
Okay.
Furthermore, the law of conservation of angular momentum, which includes both orbital and spin angular momentum, is a fundamental symmetry principle in particle physics. And this conservation law dictates which particle interactions and decays are possible and how they occur.
Now, we've touched on NMR and MRI, but our sources also highlight this burgeoning field of spintronics.
Yeah, spintronics is a really fascinating area.
What's the core concept driving that research?
So spintronics, which is short for spin transport electronics,
Right.
represents a paradigm shift in electronics. Traditional electronics relies primarily on the manipulation of the electron's charge.
Okay.
Spintronics, on the other hand,
Yeah.
aims to exploit the electron's intrinsic spin, its angular momentum, and associated magnetic moment
Wow.
as a primary means of storing, processing, and transmitting information. So the fundamental idea is to encode information using the spin state of the electron.
Right.
For example, spin up or spin down, rather than just its presence or absence, as in conventional digital electronics.
I see. So what are some of the potential advantages that spintronic devices could offer?
Well, there are several exciting potential benefits.
Yeah.
Spintronic devices could lead to significantly higher operating speeds, dramatically lower power consumption,
Right.
and the possibility of a much greater device density on integrated circuits. Additionally, many spintronic concepts offer the potential for non-volatile memory, meaning they can retain data even when the power supply is turned off,
Right.
which could revolutionize how we store and access information.
Now, our sources mention phenomena like giant magnetoresistance
Yes.
and tunnel magnetoresistance as key discoveries that paved the way for spintronics.
Right.
What are those effects?
So these are fascinating quantum mechanical effects that are observed in layered structures composed of different materials, typically including ferromagnetic metals.
Right.
Giant magnetoresistance, or GMR, is a substantial change in the electrical resistance of a multi-layered structure.
Okay.
When the relative magnetic alignment of adjacent ferromagnetic layers, separated by a non-magnetic layer, is changed. Similarly, tunnel magnetoresistance, or TMR, is a related effect where the electrical current flows between two ferromagnetic layers through a very thin insulating barrier via quantum tunneling.
Okay.
And the probability of this tunneling current depends strongly on the relative magnetic orientation of the two ferromagnetic layers. And these GMR and TMR effects are already utilized in the read heads of modern hard disk drives.
Oh, wow.
And are also the basis for magnetoresistive random access memory, or MRAM.